good problem setting, and then we can apply the numerical methods. So let's see what is a good settings for the initial value problem. So first, let's see. The things we are going to investigate is the initial value problem, and then the initial value problem, it looks like this. I just give you the very general format of the problem first, and then we are going to investigate the initial value problem, and then what is the initial value problem? Initial value problem, and then we here we have the function y, and then the derivative, first derivative of the function, and then it equals to a given source item, and then it's the f function, and then it should be a function of the time, and then the y variable itself, and also there's the initials point there. Let me see, the initial point, it should be, so there's the t variable, and then the t variable, the time variable is in the time variable is in the interval a and b. So for the initial value, it means that we are evaluating that the a, and then it equals to the for examples, we have the value let me see. I'm going to use a variable here. That is the alpha. So this is a basic setting here, but not all the initial value problem we can apply the numerical methods to approximate the solution. Only the good ones we can apply the numerical methods, and then into this class we will investigate what does the good problems look like. And so first, we need some definition. So this is the first class about the first sessions in the class. So this part is all about the existence. Maybe we can just say this is the wellposedness of the IVP. IVP, which is the shortcut for the initial value problem. And here we have wellposedness, and which means that it's a good property. And so now let's see what is the good property of an IVP. And so first, let us go back to the definition. And the definitions, the first one, it should be the definitions of the Lipschitz continuous. In case that you forget the definition of Lipschitz continuous, definition of Lipschitz continuous. And for this problem, we have the f function, and then it's in with the variable t and y, and we say a function. I'm going to use the shortcut here. The function ft(y) is Lipschitz continuous in the variable. So we just have we are just finding the Lipschitz continuous in the variable y on a set. So as you can see, this is a functions in the 2D space, and we have two variables here. So we say this function is continuous, Lipschitz continuous in the variables on a set D, and then this D is a two-dimensional space. And we say this if this is if this function satisfies the following things. If a constant L which is a positive constant, it says with the following things. And that is the ft and then y1 and then minus the ft and then with another y value, and the difference between them, as you can see, the t value are the same, but the y value, we change the y value here, y1 and a y2. And as you can see here, we are going to have the right hand side bound, and the right hand side bound, it looks like, let me see, there should be the pointer. That is the constant L, and then on the right hand side, that is the constant L times the y1 and the y2 difference. And this is the definitions of the constant continuous in the variable y for this situation. And we're, of course, we need the two variable here. It should be inside the, are in the domain D. So we also call this one as the L, and then we would call this one as the Lipschitz constant. And this is the definition, and then we define this, and because we are going to use this to have some things at below, and it's about the existence and uniqueness of the solution. So if this one, so this is the definition of the Lipschitz continuous, and then let's see, there's a theorem about the initial value problem. So I'm going to mention this. I'm going to change the order of the presentation here. This is the different order compared to your textbook. I'm going to introduce the Lipschitz continuous definition, and then now I'm going to take a look at the existence and uniqueness of the initial value problem. So this is about the existence and uniqueness and uniqueness of the solution for the IVP problem. So here this theorem, so there are several assumptions on the initial value problem. So first, this is just one version of the problem, and then we are going to investigate such a problem in the domain. You can have any other domain in the IVP problem, but in our class, we only investigate in the domain, which is, so the t and y, and the t is the time, and then it's between the a and b value, and for the y, it's along the real axis. And this is the domain we are going to propose the IVP. And we also have some assumption in the f function. That is the source item. The source item here is the f functions with two variables, and it's continuous on the D. And this is one condition on the f, and there's another conditions on the f function, and then if f satisfies the following, satisfies a Lipschitz wrong spelling, Lipschitz conditions which means that it satisfies the definitions above here. And then if the f function satisfies the Lipschitz conditions on the domain D and then in the variables Y, then the initial value problem, that is the initial value problem we just mentioned. The derivative of the y and equals to the f functions ty, and the t is in between the a and b, and we have the initial value and equals to alpha, and it has a unique solution. And yt on the domain where the t is in between the AB. So as you can see here, we have several assumptions here. All the assumption is very important in the part for the f function. So the f function first, it is continuous, which means that it's continuous in terms of the t variable. It is continuous in terms of the y variable. And also we have the second assumptions on the f function, which is the f function is Lipschitz continuous in the variable y on the domain D. And in this case, our IVP has the unique solution. And that's all the things about this existing and unique things. And any question by so far? No. And this is something you already know from the PD class. I assume that you already know that. And let's double check one thing. Let us take a look at the definitions and then check one example here. So we are going to check the, so as we can see, the Lipschitz conditions here is very important. So we are going to check one function f function, and then to see if it is Lipschitz continuous. And so there's one example here, and now we want to show this function ft(y) satisfies Lipschitz conditions on the interval. We have the domain here, and that is the t, and then this is the domain for the y. So we also need to know that it should be the Lipschitz conditions on the interval here, and then we are going to check this. And let's see. I believe that it should be the Lipschitz conditions in the variables y. So here, let's do this problem. And if we want to know the Lipschitz conditions, and then we need to do the subtraction first. And then that is the ft, and then y1 minus, and then we need to use the same t here, and then y2, and then do the difference here. And then we are going to calculate such a difference here. So we got it should be equals to the t, and then taking the absolute value, and then times the y1, and then minus the t, and then minus y2, and which equals to the absolute value t, and then taking the difference between the absolute value of y1 and y2. And which, so if you take a look at the t, and then the biggest t we can get is 2. So this one is bounded by 2, the t is bounded by 2, and then the y1 absolute value minus the y2 absolute value is actually can bounded by the y1 and then minus y to absolute value. And this is just the absolute value property here. And so as you can see, this is the it's already the Lipschitz continuous conditions. So here, hence we have F is Lipschitz continuous on the variables in the variables y with the Lipschitz constant which is 2 here. And so this is one example how to show the function is satisfied the Lipschitz conditions. And so now let's go for an another question. Let's see. So I'm going to show you one more example here, and then to check whether we have a unique solution here. So there's an example 2. So that is exactly what we are working on. And then the domain should be, the t is in between the a and b, and then the y is on the real axis. And here, we are going to use the theorem 5.4 to show there is this, a unique solution to the following question. There's this a unique solution to the initial value problem. This is a shortcut of the for the initial value problem. And then the initial value problem is y the derivative and about the t. And then we have this one is on the right hand side, the source item, it should be 1 plus t sine t y for these questions. And we have the time is in between the a and b, and then the a and b is just the 0 and 2. And the initial value is just equals to the 0. And as you can see here in the theorem statement, and it's actually, it doesn't matter what is the initial value for this IVP problem. And then the things matter is just the f function here. The f functions, we have some conditions on the f function. So we are going to double check. You are going to check the conditions on the f function, and then what is the f functions here for this problem. And this is the f function, ft(y), and then in this problem, and then we are going to check. So first is obviously this function is continuous for the variables t and y. So first, the ft(y) is continuous on the domain D. And this is the first thing. And then the second thing is we are going to get the difference between the two variables. So we are going to do the subtraction here, ft and then y1, and then minus the ft y2. And here we are going to use something you are familiar with, and that is the mean value theorem here. And let's apply the mean value theorem here. Mean value theorem, apply the mean value theorem to which variable? Apply the mean value theorem to the variable y, and then we got this. Getting the first step about the y. And then that is the first step tip. And then we want to evaluate it at the c. And actually this c is any is an arbitrary, is a point. This could see is a point in between the y1 and y2. And also because this is a mean value theorem, and then we got it is multiplying in the y1 minus y2. And this is the things. And so now let's do some calculation here before we move on to the next one. And then we are going to calculate the partial derivative here. And the partial derivative of this f function and is the partial derivative of f function regarding to the variable y. So I'm going to get the derivative, and then the first one, the first derivative of the 1 is just 0. And the derivative of the second term here, and then with respect to the y, and then it should be, so which means that we treat the t as a constant. So the t, we keep the t here, and then we are going to get the derivative of the sine function, and then it should be the cosine ty. And then because this is a composite function, and then we are going to get the derivative of the ty here, and then the derivative of ty with respect to the y is just t. So at the end of the day, the derivative of the partial f, and then the partial derivative of the function f, and then it equals to the t squared, and then cosine ty. And I would like to remind you of what we are using here. So for this one, we are using the let me see. So this is a composite function. So if you want to calculate the derivative, and then we should get the derivative of the sine function, and then times the derivative of the same sine here. And this is because this is a composite function. So now that's good. And then we have this function here, and then we are going to evaluate the things at the c here. So which means that we are going to replace the y here with the c, and then we have t squared and then cosine t c here, and then y1 minus y2. We almost get to what we want, and then that is y1 minus y2, and then actually we want to bound this function, this t squared, and then cosine t c. And actually I can add the absolute value here, and then that would be more obvious. We are getting close to the continuous Lipschitz continuous conditions. And for the t, we have an upper bound here, the t squared, and then that is 2. The biggest absolute value of the t in this interval is 2. So we can bound the t squared by 2 squared. So it's bounded by the 2 squared, and the absolute value, the biggest values of the cosine functions we can get is just 1. So that is times 1 here. And then times the y1, and then minus y2. So which is the 4, and then y1, and then minus y2. Which means that we already get to the Lipschitz conditions for this function. Hence the f function satisfies the is continuous Lipschitz continuous on the domain D. With respect to the variable y, and with the Lipschitz constant, which is 4 here. So that's all the things. And then because we have already checked the f function is continuous, and then the f function is also Lipschitz continuous on the domain y with respect to the variable y, and then with the constants, Lipschitz constant 4, and hence, so by the theorem 5.4, unique solutions exist. And this is how we apply the theorem 5.4. Any question here? So we only check two things. The f function is continuous. And then the second one is the f function is Lipschitz continuous on the variable y. And that's all the things. So this is the existence and uniqueness, and then but so far this is not good enough. Not a good enough problem so that we can apply the numerical methods. And what is a good problem? So a lot of the time, if you get a PDE, you would get something that is not very exact on the right hand side, and then you have some not very exact things for the initial conditions. And this is because you use some approximate model in your engineering rather than the real model, because you say, okay, we are going to use some model to simulate something, but you are making some simplification there, and then you have some error on the f function here, and then you also have some error on the alpha value here. But the question is that if you have such an error here, and then how well is your approximation of the solutions right? So we need the well-postness of the IVP problem such that we can use the approximation smarter numerical methods, which means that if you have some small error here and then small error here, then the solution of the y it has small error. So it could be sometimes you hear something about the butterfly phenomenon. So butterfly phenomenon, it means that if you have a small error at the initial point, and then at the end you have a very big changes at the end. But here, if we have a very good problem, and then we have some small error on the right hand side, small error on the initial item, and it does not change the y solutions a lot, and that is a good problem. So now we are going to define the well-postness of the problem. And so once again, the well-postness of the problem is all about, it's more about the how the error could affect the solutions you get. So well-postness problem. So let's see. So this is the question. So the question is that how do we determine the problem is a good problem in the following sense? How do we determine whether a problem is a good problem? A problem has the property such that the small changes or we can say that is the perturbation in the setting of the problem. Usually we would, for this IVP problems, and then we would have some perturbations at the F function, and that is the source item. And it could be happens to the F function, and then it could happens to the initial value alpha. And so how do we determine these small perturbations only introduces a small change in the solution. And this is the thing. This is the whole idea here. Wellposedness, and then the first one. So a lot of time people just get confused. What is the wellposedness? You will see the wellposedness a lot of time in the mathematics class, and I will give you some detailed definition here about the wellposedness for the IVP problem. So the wellposedness problem, and then it is saying that. So here, this is the IVP problem. And then once again, I'm going to write down the definition here. And then this is FTY, and the T is, the time is bounded time domain. And then the Y here, we investigate the Y is from -1 infinity to infinity. And we have the initial value, and it equals to the alpha. Here we said this one is a well-posed problem. Well-posed problem. If so, there's one thing about the things we just mentioned, and then it should has a unique solution. A unique solution exists. And then the second thing is about the perturbations. And that's all the things we just mentioned, but we are going to write down the perturbations, the small change corresponding to the perturbations here, perturbation. And so what's the small change corresponding to the perturbation? And it means that this is the rigorous definitions about the small change corresponding to the perturbation. So which means that there is this let me just use some words here. There is this a constant epsilon 0, and then which is bigger than 0, and a constant k which is also bigger than 0, such that for any, so here the epsilon is describing the perturbations size, such that for any epsilon, and then with the epsilon, which is inside the domain epsilon 0, and then which is also positive. So this epsilon is in between, this number is in between the constants epsilon 0 and then the 0. So here, for any epsilon in this domain, in this range, and then we have whenever delta t is continuous on the with the delta t is smaller than epsilon for all t here. So here, which means that we are controlling one part of the error, and then it's in the AB. And also when the delta t is smaller than epsilon. Then the IVP here, the IVP is with the perturbation, and then the perturbations is dy dt, and then we add the perturbations on the right hand side for the f item, and that is the delta t here. So that is the delta t we just mentioned, but it's bounded by the epsilon. And also we have, I write something wrong here. It should be the delta 0 here. Let me see. Yes, the delta 0. For the initial value, we also have the, so this is not just not the y function again, so I'm going to change the z, the variable to the z, because it's a perturbations perturbed problem. The z is with the initial value, and then with the perturbation, and then delta 0. So let me just say all the things again. So here, the perturbation. Oh, this is still working. Okay. So the perturbation here, we have some things to bound the perturbations we have, and then that is the epsilon. And then the epsilon is the bound for the perturbation, and then this perturbation should be small enough. And there's this constant epsilon 0 here to bound the perturbation altitude here. And so as you can see, if you compare to the original IVP problem, and then we just add the perturbation delta t here to the right hand side, and we also add a perturbations to the initial value alpha here. But all these perturbations we have in the source item, in the initial value term, and then the magnitude of them should be bounded by the epsilon. And this is the setting here. So if the perturbation is small, and then actually we can see that the error between the z and the true solutions y is also small. So this IVP has a unique solution. And that satisfy the so for every t the time value, we don't mind what is the t here is for the whole time domain, and then the difference between the z and y, z is just the solutions to the perturb problem, and then the y is the true solution to the problem without any perturbation item, and then this one, the error between them, or the difference between them, is smaller than the k times the epsilon for all the t in the AB. So this is very obvious, and then we just translate the words into the mathematical format, and then so in a word, which means that if we have small perturbations in the source item, small perturbations in the initial value problem, then we have a small error or small perturbations in the approximation or the solution here, the perturbed problem here. So this is a rigorous definitions for the perturbed problem, and then small change corresponding to the perturbations. And so now I'm going to give you one thing, and it's about the wellposedness of the problem. So the questions, let's see. So let's go back to here, and then our question is that how can we determine whether a problem has the wellposedness? which means that we have small changes in the setting and then which results to a small change in the solutions. So we need to determine whether the problem satisfies, whether the problem is well posed, and then we need to go back to the problem setting itself. And then the problem setting, we just have the F function and then the alpha value. So let's see. So there's a theorem about the well-posedness of the IVP, the initial value problem. And then this is a theorem 4.5 of 5.6. Theorem 5.6 is about the well-posedness of the IVP problem. So there are several assumptions here. Actually, you will find out that the assumption is quite the same as the things we have in the existence and uniqueness theorem. So we have, let me just copy down everything. Actually, the assumptions are the same, but here we have the well-posedness. So I'm going to copy all the assumption here. It's continuous, and then also the F function is it's Lipschitz continuous. Then, so if the whole problem satisfies this setting here, then the IVP problem dy dt equals to fty, and then the time domain is a and b, and then the initial value is equals to alpha. This problem is well posed, and then this is the things. So well posed, and then once again, well posed, it means that first is the uniqueness of the solution, and then the second one is the small change in the solutions corresponding to the small perturbation. And this is the well posed. You would say this is the same assumptions as the existence and uniqueness, but actually from by this assumptions about the setting, the IVP setting here, we get the well posedness. And any question by so far? It's something similar to the ODE class. We are talking about the theoretical things at the very beginning. That's because we can only apply the numerical methods to approximate the y functions for the IVP problem if the problem is well posed. And this is very obvious from this theorem because your approximations, it has the error, right? And then also, actually, if you want to do some approximations methods, later on, you will see we are going to do some Taylor expansion here. And then which means that you have some error term in this equation. If your error term is small enough, and then which means that your approximation to the solution is acceptable. Does it make sense? So which means that we require the problem to be well posed. In this case, you can make sure that your approximations to the solution, it makes sense. It's inside the acceptable error range. I see some puzzle face here. Any question? So this is why I mentioned this today, and I'm not going to show you more things than here. So the things you need to do is go back home and then take a look at the examples on the textbook, and then to make sure that you know how to check the problem is well posed. And as you can see, we just need to check the function is continuous, and then the f function is Lipschitz continuous on the domain D. And that's it for this type of problem. And in case you want to ask the questions about the domain, and I just say, in this class, we investigate the domain looks like this. Of course, you can have the domain Y and then it could be founded in other setting. But here in this class, we just mentioned this. And if you have other domain, and then I believe that the domain should be convex for the initial value problem. But here we are not investigating into other complicated domain, and then the domain, it just looks like they're a very simple one. And then if I want to draw it out, and then it's just a t here and then y here, and then the y is all the values along this real axis, and then the t is in between a and b, and then which means that the whole domain D here is just a strip on the R2. And that's a sense. And this is all the things I want to mention today. And if you have more questions, and then you can come over here. And actually, we have 1 minute left. You can ask your questions about the wellposedness of the IVP. Nothing else? Okay. We're happy about this. And then next time, I'm going to tell you the numerical methods to approximate the solutions to the IVP problem. And this is the starting point, and what kind of problems we can apply the numerical methods. And so a lot of method is based on Taylor expansion. So if you forget the Taylor expansion's formula, and then you need to go back home and then take a look at the Taylor expansion and its error term, and that's all. And you can live at this moment. Yeah, you can live for the next class. Bye bye.